Yeah. Well, let's just review, first of all, what we did last time with determinants. Okay, so the idea of a determinant is basically if you any set of vectors in a space, like if this was 3 vectors in 3 space, they define some kind of volume. I didn't draw this quite right, but to get the, well, let me just redo it. So the point's not completely there. So here's a cube, right? In which you can maybe not with the best artwork, but you can imagine a cube that is in 3 dimensions. And the idea is, say, if I have, say, the x direction, the y direction, and the z direction, so I have a basis vector in each of these directions, say e x, e y, and e z. Now, if I choose them in such an order that the basis is all where any 2 vectors on a plane, and so if you've chosen these, so that when you sweep an angle, if each one of these is counterclockwise, and this one goes back here, each one of these is counterclockwise, and you could say it's a right-handed coordinate system. And if you do this, then you can choose you can make a determinant of the column vectors of each. Like if these were column vectors, then you'd have, say, x1, x2, x3, y1, y2, y3, and z1, z2, z3. If you order them in this way, then this determinant is the area, is the volume or the area, volume, or hypervolume. Okay. So now, this is usually called a right-handed basis. And it has to do with the connection between the basis elements and the geometry of arrows in Euclidean space, right-handed basis. So this area or volume connection has to do with that. Now, if you interchange 2 rows over here, then you change this, you can get a positive, this will become a negative. Like if I interchange these rows, these columns rather, where the book was to, if I interchange 2 columns, which is switching 2 vectors, then it changes the sign of the area. And so there's ways to define this counterclockwise direction, in each case, but this is the basic idea. And so this is sort of the conceptual origin of the determinant. And what you've chosen is the volume in this connection. You've chosen the volume to be defined by the 3 vectors to be a parallelepiped or a parallelogram or whatever, parallelepiped. And you've chosen that because then the properties of the area or volume act nicely with row operations. So then we just say, okay, well, let's just take that as something we want, and we set the properties of this properties of decision to use area, volume, of this particular shape, parallelepiped. I think that's the right. There's too many L's and P's. But I think that's what it's called if it's in higher volumes. But as two-dimensional as a parallelogram. The point is that you end up then with if the determinant of A equaling the if you have a row operation like R row I plus row J, determinant of A prime. And we'll also use the notation of sort of you reuse again the absolute value notation because that's easier to write than the writing DET all the time. Okay, so that means that doing row operations doesn't change the value of the volume or area. It doesn't change the value of the determinant. On the other hand, though, scaling does. So what we say is the determinant of A scaled up, right? So what we're going to, this would be like R times row I. If I scale it by R, then it's R times the determinant of A prime. A prime is the new one, the one after the operation, after row operation. Okay, so this connects this up, but this one's easy. So what you can do it practically, that the effect is that you can factor a common factor out of a determinant. So this is a little bit, in other words, this is sort of the way you use this is to take a determinant of a matrix, factor out a row, and you can just pull it out. And the same way here, if I do a row swap, this can be a minus sign. So what happens is if I do the row operation here, the only one that's sort of unusual is that we sort of use it a different way than the formula suggests, is to sort of factor out, like in some sense, we use it the other way around. We start from this one, and that's good, and we factor out the R to get this one. So this is the smaller determinant here. So we sort of use it the other way around when we write it down. Okay, but so you have the same row operations, which basically means you can calculate determinants with Gauss's method. So let's practice say that. And there's a number of consequences of this. Let me just list the major consequences. DT always exists for any matrix, and it is unique in the sense that given these three properties, along with the property, there's sort of like 1, 2, 3, 4, along with the fact that determinant the identity is as a normalization defining 1, given this, the determinant's unique. So that's sort of a major consequence. There's several minor consequences, such as that if a matrix has if it has a 0 row, then it is if it has a 0 row, a determinant 0, because I can take that 0 row and factor out a 0 in front of it, and that's why I get 0. And similarly, if I have two rows that are the same, I can use a row operation that adds one, that subtracts one row from the other row to create a 0 row. So that works the same way. And you can also show that the determinant of a transpose is equal to the determinant, which means if any columns are the same, you have the determinant 0. So if any rows or columns the same, the determinant is zero. And a crucial, sort of a really useful property is the determinant of a product of matrices is the product of the determinants. So you have all these little, like you have that the determinant, let me use the simple notation, AB equals A times B, and you can, one application of this is the fact that you can show that the determinant of the inverse is 1 over the determinant of the matrix. And you notice that this is related to the fact that the inverse only exists if A is not equal to 0, which would be required for this to happen, because otherwise you couldn't divide by 0. Okay, and then also the determinant of a transpose equals the determinant of that. Okay, so those are some useful properties of determinants in general, which you can use to simplify things. And in fact, what you can see is that since you only define determinants for square matrices, this is only defined for square matrices. Square meaning that the number of rows is equal to the number of columns. Only defined for square matrices. Number of rows equals number of columns. And when you get around to it, you can see that the determinant of a diagonal matrix, that is that the only non-zero entries are along the long diagonal, equals product of diagonal entries. And because the row operation doesn't, because the row combination operation doesn't change the determinant, and to go from echelon form to reduced echelon form only involves the row combination operation. So as a result, the determinant of an upper triangular matrix also equals product of diagonal entries. So that means that all you have to do is get your matrix to echelon form, and then you know what it is. So basically, it really is just Gauss's method. That you don't have to use you don't have to go to reduced echelon form. Once you get to echelon form, you know the answer. There's a product of diagonal entries. And you can see right away, if you have, thinking of a coefficient matrix, thinking of the matrix as a coefficient matrix of a linear system, but if the determinant is 0, that means that one of the entries along the diagonal entries is 0, and the only way that can occur is if it's at the bottom of the matrix. If you can't have a 0 on the diagonal in the middle of the rows, because that would mean the row with a 0 it would be shorter than the row below it, so it wouldn't be in echelon form. So all the zeros, if you have a 0, it's got to be at the end of the matrix, which means you have a 0 row. So the point is, if there's a connection between having if the determinant 0, the only way that can occur is if there's a free variable, which means the matrix is singular, which also means it doesn't have an inverse. So anyway, you can sort of connect up all these different properties. So let's just practice this with, let's see, who we have here, 11, 44, 66, and say 8. Let's see, 24 and 64, and say 4, 8, and 6. What's the determinant of this matrix? So use row operations. Now you write 11, 44, 66, 8, 24, 64, 4, 8, 6 to figure out what the determinant of this matrix is. And then we'll go back over it.